Hello, everybody. Welcome to Power Corner. I'm your host, Ali Ashokath, Editor-in-Chief of Power Electronics News. Today, we're speaking with Mike Sandyck, Marketing Director at Cissoid. How are you doing, Mike? Thanks for meeting with me.
Very good. Nice to be
Great.
here.
Yeah, so I mean, we could start off by accompanying covering Cissoid as a company.
Mhm.
Maybe you could cover Cissoid's origins and why choose the high temperature power electronics niche.
Sure. So, Cissoid was spun off the University of Louvain-la-Neuve, close to Brussels, in July 2000. So we've been around a while, and that was due to indeed research in high temperature semiconductors. So the legacy business of Cissoid is indeed in high temperature and performance electronics, where we had components that were tested by NASA from minus 200 degrees to plus 400 degrees C and still
Oh,
functioned
wow.
for hours on end. So not just for a few minutes, but long durations. Yes, so the early business until last year, when the process that the devices were built on was stopped, was really going into applications that were running, and we guaranteed that they were running up to 225 degrees C for 5 years on end. So continuous high temperature applications, be it in avionics, in aerospace applications, defense applications, oil and gas, so stuff that goes down the borehole at very high temperatures, continuous running. That was the typical business of Cissoid. And about 2008, 2009, they started to see the advantages of silicon carbide exactly in the high temperature capabilities of the technology and started to adopt it. And quickly noticed that it wasn't easy to drive those devices, so developed our own gate driver chipset for it. And that's what started the whole silicon carbide story really rolling at Cissoid. So we've got more than 16, 17 years of experience driving silicon carbide. So we've learned a thing or two over the years.
Yeah.
And along that route, started to develop more complex modules with their own gate drivers, with their own control systems, and so on. So that's the business we've been transitioning to in the last couple of years.
Yeah, thank you. Thank you for kind of giving me the bigger picture there. I was wondering, I mean, I know this is very broad subject, so explain what you can, but what are some of the major considerations when designing high temperature gate drivers and power modules all the way up to those intelligent control modules?
Well, what we do a little bit different at Cissoid than at the major competitors is that we always design for high temperature capability across the whole temperature range. So it's one thing to make a component perform at 25 degrees C where it's specified, but doing the same thing in continuous operation at high temperatures is quite another thing. So that's really where the knowledge and expertise from Cissoid comes into play, and
Mm,
also how to build a component that lasts through heavy duty application.
mm, gotcha. Um, Now, so you were saying that the driving silicon carbide wasn't easy, and that's what inspired I believe it's the HADES gate drivers, and uh, that's where Cissoid's expertise in silicon carbide really originated back in 2008 to 2009,
Mm.
as you were saying, um, and I understand that product line was dependent on the X-FAB Xi10 process, which was discontinued. And from what I read, it impacted the CHT, CMT, and CXT product lines, which, from what I understand, are based on the original HADES gate driver chipset, and that's being phased out. And when we chatted at PCIM, you mentioned that that wasn't necessarily a bad thing, and that it was an older process, so it wasn't exactly cost effective. I was wondering, maybe you could talk about that a little bit more, and what's Cissoid doing in place of that.
Yeah, sure. So we did have already a third generation of the gate driver in the planning, but we accelerated that due to the obsolescence of the process. And yes, that was and is a unique process that isn't done anywhere else, which provides that continuous high temperature capability. Now we've ported the design to a more modern process, so it's more performant, more cost effective, yielding a more compact solution. And we've taken the opportunity to improve a few things, but we've kept the extensive functionality and protections that were on board. So it's basically more of a porting exercise and updating rather than adding functionality. But yeah, what we've seen, especially with the intelligent power modules that use these drivers, is that with the protections already in the hardware, we see a lot of cases where something happens in the electromotor and the drive shuts down before anything drastic happens. So it's really helpful to have all those protection and hardware.
So it can run continuously without those unwanted or unpredictable shutdowns.
Yes.
Okay. Thank you. And the new HADES line, as you were saying, that the new generation is more of a porting exercise, so it'll have the same sort of high temperature capabilities, same functionalities. Am I correct in assuming that?
It's not going to go up to 225 degrees C, but 175, which is more typical with the current processes. But that's sufficient for the majority of the applications we go into. So far, we don't have the business case yet to revive the 225 degrees process. But yeah, we'll see what the future brings there.
Yeah. Yeah. Okay. Yeah. And maybe we can move on to the intelligent power modules. I was wondering how that line began. And you just mentioned this. It was and you also, when we talked during PCIM, you said that it started in Cissoid's work with the hybrid electric aircraft. Could you talk about that a little bit more, the intelligent power modules?
Yes. So we started to make driver boards specific for certain power modules with our gate drivers. And then due to customer demand, we developed a three-phase power module. And this was already back in 2016, so 10 years ago. We released that module with the gate drivers on top of it. So there's, at my knowledge, nothing in the market like it, certainly not with silicon carbide. There's one or two versions with IGBTs that have the gate drivers on top of it, but yeah, silicon carbide is a more sophisticated to drive, requires better handling, and yeah, can really make use of having the gate drivers on board. Now, this is also again where the Cissoid products stand out a little bit. The whole module is certified to 125 degrees C, where typically it's only 75 for the PCB assembly or 85 if you're lucky. So we really design for high temperature capability. Which again plays into heavy duty and rugged and robust applications.
And that as you're saying, that's really, you're saying that there's not many competitors in the market, and that primary differentiating factor is that high temperature functionality, continuous performance at high temperature. Yeah. maybe we can talk about sort of the relevant specs around the IPMs. I understand there's, that it has a VDS of 1200 volts, and then there's a max DC current rating ranging from 340 amps up to 550 amps at case temperature of 25 C. Was there anything else that you wanted to kind of explain about the IPMs and their specifications that are just really relevant for the customer to know?
Oh, yes. So the 1200 volt is due to silicon carbide dies being used of 1200 volt capability. And depending on the current rating, we parallel more or less devices within the modules. So that's what brings the range of current capability that you can do with those modules. Yes.
Yeah. I noticed that there was the aluminum silicon carbide pin fin base plate. And maybe you could talk about the performance improvements using that over the flat base plate
Okay, so
for
there's a
the
couple of
intelligent power
aspects
modules.
there.
Yeah.
Sure.
Yeah.
There's a couple of aspects there. The flat base plate is really for applications where the designer wants to use a different cooling system than liquid cooling or another type of system. Typically, it's air cooled, so it's also the version available in the lower power range and the lower current capability. Because you get an additional thermal transfer layer between the cooling plate or airflow that needs to go next to it. So you have higher current capability with the pin fin based. And the other one is the choice of material. Because we use AlSiC for the base plates, it has a couple of properties that really lift it above copper. Copper conducts heat better, but the weight to conductivity ratio of AlSiC is a lot better. So you get a little less thermal transfer, but you get a more rigid base plate. And most of all, the thermal expansion of AlSiC matches much better that of silicon and the ceramic compounds. So, for example, the ceramic substrate attached to the heatsink will expand and contract with thermal cycling in a much more similar rate as the base plate as you have with copper. So you get less stress on the connections.
I see.
Again, to improve ruggedness with heavy thermal cycling.
May I ask what the ceramic what's the ceramic used in the IPMs then?
Yes, it sits below the MOSFET switches to isolate them to electrically isolate them from the base plate so that you don't connect 1200 volt to the chassis of your vehicle, for example.
Is it potentially alumina or silicon nitride or what's
Yes,
the okay, yeah.
it's one of those compounds.
Okay, gotcha. Sorry. um, and so in the future, will the third generation of these the gate drivers be implemented in sort of a next generation IPM solution? And I'm sure there's plans on that.
Yes, absolutely. They're actually serving as the evaluation platform for the new chips. So they are currently being used to redesign the gate driver boards. That's correct.
Okay. So maybe we can move on to unless there's something else that you wanted to cover, say with the gate drivers or the IPMs. I was going to move on to the inverter control modules.
Maybe just one point in why using AlSiC versus copper is also the weight.
Oh, yeah.
Because copper is about 9 grams per cubic centimeter, and AlSiC is a third of that. So we get about 25% weight savings in the module, which is much appreciated in a lot of applications. Certainly it fits airospace.
Yeah. You always got those swap C constraints that you have to worry about, right?
Yes.
So the ICMs, the inverter control modules, I believe, how do these complement the intelligent power modules, and what does it add that might be difficult for a company to obtain with their own controller?
Sure. So the inverter control modules are the next step in getting closer to a motor control system. So they add on the stack of the power module, the gate driver board, and on top of that there's a motor control board. So it adds a layer of complexity. It again makes the life easier of designing a motor control system because it has the processor and software already on there. It's automotive qualified, it's functional safety certified. So it takes away a lot of headaches from design engineers. And there's a lot of complexity in both the drive, in the hardware, and in the software, making it as efficient as possible, but also fault tolerant and very high functional safety.
Yeah, it was ASIL-D, right? Or
yes. So the processor and the software are ASIL-D certified, and the module is ASIL-C ready certified at the moment. We're moving across to get it fully ASIL-C certified. But yes, that's really the level we're working at.
Okay, yeah. I wanted to know what drove the choice in processor in the inverter control modules. Maybe we could talk about that a little bit.
Well, yeah, it's mainly an application-specific processor. It's really designed to control motors, and in that respect, it has several hardware features that are very unique. For example, it has a FPGA-like structure in it, meaning that a lot of the motor control loop is implemented in hardware. So you get very fast reaction time, something that you cannot obtain in software running on a core. So we've got reaction times in the tens of nanoseconds when anything happens within the motor. And yeah, as mentioned, we've got calls from developers saying, "Oh, your drive is shutting down," and when eventually it appears that something happened within the motor that made the drive shut down. But yeah, that's a kind of capability that the processor brings, which makes the pretty unique solution.
Yeah. Maybe you could talk more about the control algorithms for the torque, speed, current, and rotor. I saw that on the website. Yeah.
Well, I'm no expert there, but we do offer a very wide range of modulation schemes and motors that we can address with it. And indeed, we can offer both torque, speed, and current control, which is not so common within motor drives.
Actually, I mean that is quite a broad range. You know, we're talking about, you know, the gate driver chipset to the intelligent power module to, you know, inverter control and the control algorithms, you know, implemented in there. I mean, that's quite a wide range of capabilities. I wanted to talk about that the engineering services, right? And you know, when we chatted during PCIM, you mentioned that Cissoid formally launched their engineering services, and that roughly half of the business is custom products, with or without engineering services later. And you know, what's the split between the two? Could you just talk about like the custom services a little bit more?
Sure. So we've been doing it forever, you know, from making ASICs, so very specific ICs designed specifically for one customer, up to, on the other end, derivatives of standard products. The one change is that we haven't really put outward that we do offer those services. It usually comes up within the conversation when a standard component can't cut it, that we then offer, oh, look, we could do this or that to solve your problem. And that ranges, as I said, from a fully custom device, either a power module or a completely functional module, custom designed for that application, up to a chip really designed for that application. And where we draw the line in offering engineering services is that the business model is really to help implement devices that Cissoid can produce. So we won't offer engineering services to do a software development specific just for that application at the customer if we cannot supply the hardware.
I
So
see.
that's really the model that's behind it.
Okay.
It ranges indeed from a customized standard product where there's very little engineering involved to a full custom product where obviously there's quite some engineering involved, and then the services are supplied for a fee.
Yeah. Do you think you might be able to give an example, where about the engineering services, where it might start and stop? Could it be limited to adapting the existing silicon carbide and IGBT, which I will get around to the IGBT soon, but platforms, or do you adapt those existing platforms, or does it extend to the fully custom silicon, as well? So do you have an example of this?
Yes, for example, we have a
Yeah.
power module in production that's specifically designed for a customer. It's only used for that customer. And it has a control system using our gate drivers on top of it. So it's a fully functional, intelligent power module for a very specific application. And that's a custom design.
Yeah.
Uh,
Yeah.
really made for that project.
Okay. And I think I'm bouncing around here, but unless there's something else you wanted to mention for the engineering services, I was gonna just shift to the IGBT power modules as well. But
That's
please let
fine.
me know if there's anything you wanted to add before I do that shift.
No, that's okay. I think
Okay.
we've covered it.
Okay. So I saw, there was the news at PCIM, the new IGBT power module families. Can you talk about this lineup a little bit more? Because Cissoid doesn't only do silicon carbide, but also IGBT power modules.
Yes. So we're, as mentioned then, we're more formally splitting the business in units going power semiconductors, power systems, and engineering services, where, of course, the historical business and pillar is power semiconductors.
Yeah.
And IGBTs are still 90% of the market, if I'm not wrong. So they're still there, and they will still be there for quite a long time. So we felt that we needed to fill some gaps in our offering there, simply because the demand is still there.
Mm.
And in that respect, we've been releasing several form factor IGBT modules.
Yeah, and I mentioned you mentioned that they're both hardware and software customizable, and that the modules could be arranged up or down in power depending upon the application. Do you think you might be able to give an example of how this customization can help a customer application?
Well, it comes back to the IPM story. And to us, it doesn't really matter if it's an IGBT power module beneath it or a silicon carbide one.
Yeah.
That's really driven by the customer demand. Where we see IGBTs chosen over SiC is mainly due to cost. Where it's a very cost-sensitive application, there the choice tends to go to IGBT. If they don't really care about the efficiency that much and the cost is the main driver, then that's where the choice goes to IGBT at this point.
Gotcha.
But indeed, if we add the gate driver board on top of that and a control board and create a inverter control module based on IGBT, that's fine by us. It really is project dependent.
Yeah. Okay. And I understand that these are built on trench gate field stop technology. Can you describe what this is and maybe the benefits of using this in high temperature and high reliability applications?
Sure. So there's two elements to that. You've got the trench gate, which instead of a planar gate, which is flat, created on top of the device. The trench is a narrow vertical channel created within the device, and the advantages there is that you get better control of the current, you get better current flow there, you get more rugged behavior, it's more stable, it's less sensitive to perturbations. So you get a more rugged design with the trench gate. And on the other side, the field stop layer is a buffer layer built into the device at the very bottom, just above the collector. That really truncates the electric field in the device, meaning you can make it smaller. So you can reduce the height of the device itself. So you get better thermal performance, you get better conductivity, and so on. So yeah, you get a lot of cumulative advantages in reducing switching losses, in reducing conduction losses, in higher power density, more ruggedness, and so on.
Perfect. I don't think I have any more questions outside of that. I mean, we could talk more about the IGBT technology, but was there anything that you wanted to cover there?
No, I think that about covers it. The range is gradually still expanding. We've got a few devices that are being released in the next months. So yeah, we're really following the customer demand there.
Yeah. So that's so more IGBT products and the potentially the gate driver, the new gate driver chipset. That's already being tested. So I think that I remember when we spoke, you said potentially early next year. So that's exciting. Was there before I close things out? Was there anything that you wanted to that I might have missed? Any last comments?
Maybe just something we're proud of at the gate driver design is that it was a first-time right design. So
okay,
we're pretty happy about that one.
yeah, that's great. Well, thank you so much for taking out the time to speak with me, Mike. Considering the time difference as well, so I do appreciate it.
It's always a pleasure. Thank you, Ali.
Thank you.